Section 250.8 of the National Electrical Code addresses the connection of grounding and bonding equipment. The purpose of this section is to ensure that grounding and bonding connections are mechanically sound and provide a low impedance path for fault current. This is crucial for electrical safety and proper operation of overcurrent protective devices. Grounding conductors and bonding jumpers must be connected in a way that provides a reliable and permanent electrical connection. This connection must be able to withstand the mechanical stresses and environmental conditions that are likely to be encountered. The code explicitly states that sheet metal screws shall not be used to connect grounding and bonding conductors or connection devices to enclosures. The reason for this prohibition is that sheet metal screws do not provide a reliable and permanent connection. They are prone to loosening over time due to vibration, corrosion, and thermal cycling. This can result in a high-resistance connection, which can impede the flow of fault current and create a safety hazard. The term bonding is used to establish electrical continuity and conductivity between metal parts that are likely to become energized. Bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of electric shock. Bonding is typically achieved using bonding jumpers, which are conductors that connect two or more metal parts together. These jumpers must be sized and installed according to the requirements of the NEC. Acceptable methods for connecting grounding and bonding conductors include the following. Firstly, exothermic welding, which involves a chemical reaction that creates a permanent metallurgical bond between conductors. This method is often used for grounding electrodes and underground grounding systems. Secondly, listed pressure connectors, which are mechanical connectors that are designed and tested for grounding and bonding applications. These connectors must be listed by a recognized testing laboratory, such as UL or ETL. Thirdly, terminal bars, which are metal bars with multiple connection points for grounding and bonding conductors. These bars are typically used in electrical panels and equipment enclosures. Fourthly, pressure-type wire connectors, which are similar to listed pressure connectors, but they are typically smaller and used for connecting smaller gauge conductors. Fifthly, other approved means such as compression connectors, set screw connectors, and bolted connections. Any connection method used must be listed and labeled for grounding and bonding purposes. When making grounding and bonding connections, it is important to clean the surfaces of the conductors and enclosures to remove any dirt, corrosion, or other contaminants. This will ensure a good electrical connection. It is also important to tighten the connectors to the proper torque specified by the manufacturer. Over-tightening can damage the connector or the conductor, while under-tightening can result in a loose connection. In addition to the general requirements for grounding and bonding connections, there are also specific requirements for certain types of equipment and installations. For example, Section 250.104 of the NEC covers the bonding of metal water piping systems. This section requires that metal water piping systems be bonded to the building grounding electrode system to prevent them from becoming energized. Section 250.118 lists the types of equipment grounding conductors, which include wire-type, cable-type, and metal raceways. The equipment grounding conductor is used to connect the metal parts of electrical equipment to the grounding electrode system. Section 250.122 specifies the minimum size of equipment grounding conductors. The size of the equipment grounding conductor must be based on the size of the overcurrent protective device protecting the circuit. Section 250.130 covers the methods for grounding equipment on separately derived systems. A separately derived system is a source of electrical power that is not directly connected to the utility power grid, such as a generator or a transformer. The grounding requirements for separately derived systems are different from those for systems that are directly connected to the utility power grid. The NEC also provides specific requirements for grounding and bonding in hazardous locations. Hazardous locations are areas where there is a risk of explosion or fire due to the presence of flammable gases, vapors, or dusts. The grounding and bonding requirements for hazardous locations are more stringent than those for non-hazardous locations. This is because a spark from a poorly grounded or bonded connection can ignite a flammable atmosphere. In summary, Section 250.8 of the NEC is an important section that covers the connection of grounding and bonding equipment. This section prohibits the use of sheet metal screws for connecting grounding and bonding conductors or connection devices to enclosures. It also specifies acceptable methods for making grounding and bonding connections. By following the requirements of this section, you can ensure that grounding and bonding connections are mechanically sound and provide a low impedance path for fault current. This will help to protect people and property from electrical hazards. The grounding electrode conductor connects the system grounded conductor to the grounding electrode. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the service entrance conductors. The grounding electrode system consists of one or more grounding electrodes that are used to connect the electrical system to the earth. Common types of grounding electrodes include metal water pipes, ground rods, ground plates, and concrete encased electrodes. The NEC specifies the requirements for the installation of grounding electrodes, including the minimum length and depth of ground rods and the minimum size of ground plates. The purpose of bonding is to create a low impedance path for fault current to flow back to the source. This allows the overcurrent protector device to quickly trip and energize the circuit. Bonding is typically achieved by connecting all metal parts of the electrical system together with bonding jumpers. The size of bonding jumpers is determined by NEC Section 250.102. The NEC also provides specific requirements for bonding different types of equipment, such as metal water pipes, gas pipes, and structural steel. These requirements are designed to ensure that all metal parts are properly bonded and that there is a low impedance path for fault current to flow. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electric shock. GFCIs work by monitoring the current flowing in the circuit and tripping if there is a difference of 5 mA or more between the current flowing to the load and the current returning from the load. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or RFCIs, are devices that are designed to protect against fires caused by arc faults. Arc faults are dangerous electrical faults that can occur when insulation breaks down or when wires become loose. RFCIs work by monitoring the current flowing in the circuit and tripping if they detect an arc fault. RFCIs are required in many locations, such as bedrooms and living rooms. Surge protective devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges are brief spikes in voltage that can damage or destroy sensitive electronic equipment. SPD work by diverting the surge current to ground. SPD are recommended for all electrical systems, especially those that serve sensitive electronic equipment. Understanding impedance is very important for grounding and bonding. Impedance is the total opposition to current flow in an alternating current circuit. It includes resistance, inductive reactance, and capacitive reactance. A low impedance grounding and bonding system is essential for providing a safe path for fault current to flow back to the source. This allows the overcurrent protective device to quickly trip and energize the circuit. A high impedance grounding and bonding system can impede the flow of fault current and create a safety hazard. Regularly inspect the grounding and bonding system to ensure that all connections are tight and free of corrosion. Any loose or corroded connections should be repaired or replaced immediately. Test GFCIs and RFCIs regularly to ensure that they are functioning properly. Replace any GFCIs or RFCIs that fail the test. Consider installing surge protective devices to protect electrical equipment from voltage surges. Have a qualified electrician inspect the electrical system periodically to ensure that it is in good condition and that it meets all applicable codes and standards. Proper grounding and bonding is essential for electrical safety. By following the requirements of the NEC and taking the necessary precautions, you can help to protect people and property from electrical hazards. The NEC is a complex document, and it is important to consult with a qualified electrician if you have any questions about grounding and bonding.